Article 300.3 B2 of the National Electrical Code states that a grounding conductor installed on the outside of a conduit cannot exceed 6 feet in length. The National Electrical Code does not specify a length limit for a grounding conductor used to ground a transformer to building steel in Article 300.3 B2. However, other sections of the National Electrical Code may apply. These other sections are detailed here. Article 250.122 addresses that the grounding conductor must be properly sized to carry the fault current that can flow through it. Article 250.118 speaks to the fact that the grounding conductor must be continuous, with no splices or joints, unless properly made. The limitation on the length of the grounding conductor on the outside of conduit is primarily due to the potential for voltage drop and increased impedance. For grounding transformers, the length of a grounding conductor is less critical because the transformer is directly connected to the building steel, which provides a low resistance path to ground. Furthermore, transformer grounding is typically designed by an engineer who considers the specific application and calculates the required conductor size and length. The rationale behind limiting the length of an external grounding conductor on a conduit stems from concerns about impedance and voltage drop. A longer conductor presents a higher impedance path for fault currents, which can impede the rapid clearing of a fault. This delay can increase the potential for equipment damage and electrical hazards. In contrast, when grounding a transformer directly to building steel, the steel structure itself provides a very low impedance path to ground. This inherent low impedance minimizes voltage drop and ensures effective fault current dissipation, making the length of the grounding conductor less critical. The size of the grounding conductor plays a crucial role in ensuring electrical safety and proper system operation. If the conductor is too small, it may not be able to handle the fault current, leading to overheating and potential fire hazards. Conversely, an oversized conductor can be unnecessarily expensive. The National Electrical Code provides guidelines for sizing grounding conductors based on the size of the overcurrent protection device protecting the circuit. These guidelines ensure that the conductor has sufficient capacity to safely carry the maximum fault current. The material of the grounding conductor also affects its performance. Copper is the most common material due to its excellent conductivity and corrosion resistance. Aluminum is also used in some applications, but it has a lower conductivity than copper and requires larger sizes to achieve the same ampacity. The type of insulation on the grounding conductor is also important, especially in wet or corrosive environments. Proper insulation prevents short circuits and ground faults. The connection of the grounding conductor to the equipment and the grounding electrode system must be properly made to ensure a low impedance path for fault currents. Loose or corroded connections can significantly increase impedance and impair the effectiveness of the grounding system. Grounding electrodes are typically made of copper or galvanized steel and buried in the earth to provide a direct connection to ground. The type and number of grounding electrodes required depend on the size and type of electrical system. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. The National Electrical Code specifies the minimum requirements for grounding electrodes, including their size, depth, and spacing. These requirements ensure that the grounding electrode system has sufficient capacity to dissipate fault current safely. The grounding electrode system must be properly maintained to ensure its effectiveness. Corrosion and physical damage can degrade the performance of the grounding electrodes over time. Regular inspections and maintenance are necessary to identify and correct any problems. Proper grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault currents, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding ensures that all metal parts of an electrical system are at the same potential, which eliminates voltage differences that can cause electrical shock. The National Electrical Code provides comprehensive requirements for grounding and bonding. These requirements are based on decades of experience and research and are designed to protect people and property from electrical hazards. Proper grounding and bonding are not just a matter of code compliance. They are also a matter of good engineering practice. A well-designed and properly installed grounding and bonding system can significantly improve the reliability and safety of an electrical system. The National Electrical Code, or NEC, serves as the cornerstone for electrical safety in the United States. It is a comprehensive set of standards that govern the safe installation and maintenance of electrical wiring and equipment. Compliance with the NEC is not just a matter of best practice. It is often a legal requirement enforced by local and state authorities. Understanding the NEC is essential for anyone involved in electrical work, from electricians and contractors to engineers and inspectors. The NEC is updated every 3 years to reflect the latest advancements in technology and safety practices. Staying current with the latest edition of the NEC is crucial for ensuring electrical safety. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding and bonding, and equipment installation. It also includes specific requirements for different types of occupancies such as residential, commercial, and industrial buildings. The NEC is organized into chapters, articles, and sections. Each section contains specific requirements for a particular aspect of electrical work. The NEC uses a numbering system to identify each section. For example, Section 300.3. B2 refers to a specific requirement in Article 300, Part 3, Subpart B, Item 2. The NEC also includes tables and figures that provide additional information and guidance. These tables and figures are often referenced in the text of the code. The NEC is a complex and detailed document. It can be challenging to understand and apply, but numerous resources are available to help. These resources include training courses, seminars, and online forums. Many organizations offer NEC training and certification programs. These programs can help electricians and other electrical professionals develop the knowledge and skills they need to comply with the NEC. The NEC is not a substitute for sound engineering judgment. It provides minimum requirements for electrical safety, but it is up to the engineer to design a system that meets the specific needs of the application. The NEC is constantly evolving to reflect changes in technology and safety practices. Staying current with the latest edition of the NEC is essential for ensuring electrical safety. Grounding systems are designed to provide a low impedance path for fault currents to return to the source. This low impedance path helps to trip over current protection devices and prevent electrical shock hazards. There are several different types of grounding systems, including grounded, ungrounded, and impedance grounded systems. Grounded systems are the most common type of grounding system. In a grounded system, one of the conductors is intentionally connected to ground. This conductor is called the grounded conductor or neutral conductor. Ungrounded systems do not have any intentional connection to ground. Ungrounded systems are sometimes used in industrial applications where a high degree of reliability is required. Impedance grounded systems use an impedance, such as a resistor or reactor, to limit the amount of ground fault current. Impedance grounded systems are often used in applications where it is important to minimize the damage caused by ground faults. The grounding electrode system is the part of the grounding system that provides a direct connection to earth. The grounding electrode system typically consists of one or more grounding electrodes. Grounding electrodes are typically made of copper or galvanized steel and are buried in the earth. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. The bonding system is the part of the grounding system that connects all metal parts of the electrical system together. The bonding system ensures that all metal parts are at the same potential, which eliminates voltage differences that can cause electrical shock. The bonding system typically consists of bonding jumpers, bonding conductors, and equipment grounding conductors. Bonding jumpers are used to connect metal parts that are not directly connected to each other. Bonding conductors are used to connect metal parts to the grounding electrode system. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding electrode system. Grounding and bonding are essential for electrical safety. A properly designed and installed grounding and bonding system can significantly reduce the risk of electrical shock and fire hazards. The National Electrical Code provides comprehensive requirements for grounding and bonding. These requirements are based on decades of experience and research and are designed to protect people and property from electrical hazards. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance. Voltage drop can be a significant problem in electrical systems, especially in long circuits or circuits with heavy loads. Excessive voltage drop can cause equipment to malfunction and can even damage equipment. The National Electrical Code provides guidelines for minimizing voltage drop. These guidelines recommend limiting voltage drop to 3% for branch circuits and 5% for feeders. There are several ways to reduce voltage drop in an electrical system. These include using larger conductors, shortening circuit lengths, and reducing loads. The impedance of a conductor is its opposition to the flow of alternating current. Impedance is made up of resistance and reactance. Resistance is the opposition to the flow of current caused by the material of the conductor. Reactance is the opposition to the flow of current caused by the inductance and capacitance of the conductor. The impedance of a conductor increases with frequency. This means that voltage drop is more of a problem in alternating current circuits than in direct current circuits. Fault current is the current that flows during a short circuit or ground fault. Fault current can be very high, often thousands of amps. It is important to protect electrical systems from fault currents to prevent equipment damage and electrical shock hazards. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical systems from fault currents. Overcurrent protection devices are designed to trip and interrupt the flow of current when a fault occurs. The size of the overcurrent protection device must be properly selected to protect the circuit from overcurrents and fault currents. The National Electrical Code provides guidelines for selecting the proper size of overcurrent protection devices. Coordination is the process of selecting overcurrent protection devices so that the device closest to the fault trips first. Coordination is important to minimize the extent of the outage caused by a fault. Selective coordination is a type of coordination that ensures that only the overcurrent protection device closest to the fault trips. Selective coordination is often required in critical applications such as hospitals and data centers. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current of 5 mA or more, the GFCI trips and interrupts the flow of current. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or FSIs, are devices that are designed to protect against fires caused by arcing faults. Arcing faults are a type of electrical fault that can generate high temperatures and ignite nearby materials. FSIs monitor the current flowing in a circuit for signs of arcing. If an arcing fault is detected, the FSI trips and interrupts the flow of current. FSIs are required in many locations such as bedrooms and living rooms. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are sudden increases in voltage that can damage or destroy electrical equipment. SPD work by diverting the surge current to ground. SPD are available in a variety of types and sizes. Type and size of SPD required depend on the application and the level of surge protection required. Electrical safety is a serious matter. It is important to follow all applicable codes and standards to protect yourself and others from electrical hazards. If you are not qualified to perform electrical work, you should hire a licensed electrician. A licensed electrician has the knowledge and skills to perform electrical work safely and properly. The National Electrical Code is a living document that is constantly being updated to reflect changes in technology and safety practices. Staying current with the latest edition of the National Electrical Code is essential for ensuring electrical safety. Continuous professional development and continuous learning is paramount in electrical safety.